and solve given problems related to projectile motion. Now let's first define projectile motion. Projectile motion is two-dimensional motion under constant acceleration, or when a body is thrown vertically upward when it follows a curved path. Projectile refers to an object upon which the only force acting is gravity, while trajectory is a parabolic path of a projectile. A sample picture of a types of projectiles. For this lesson, we will be encountering two projectile motions, namely horizontally launched projectile and non-horizontally launched projectile. For horizontally launched projectile, it is defined as a projectile launch with an initial horizontal velocity from an elevated position and follows a parabolic path to the ground. See this cannon releasing cannonballs. And for non-horizontally launched projectile, it is a projectile launch at an angle to the horizontal and rises upwards to a peak while moving horizontally. Looking at this picture is a baseball player kicking a ball with an angle. These are the kinematic equation we will be using for projectile motion. We have the kinematic variables, namely d, this is for displacement, t for time, a for acceleration, v for velocity, vi for initial velocity, and bf for final velocity. Now for the first kinematic equation, we have displacement is equal to initial velocity times time plus 1/2 times acceleration due to gravity times time squared. Second, we have final velocity squared is equal to initial velocity squared plus 2 times acceleration due to gravity times displacement. We also have final velocity is equal to initial velocity plus acceleration due to gravity times time. And for our last equation, we have this displacement is equals to initial velocity plus final velocity over 2 times time. Now, take note that we decide which kinematic equation is best for what we are solving. So generally, kinematics problems involves solving for some unknown. So the unknown could be initial displacement, final displacement, change in displacement, initial velocity, final velocity, acceleration, or time. So we can choose any of the equation depending on what is given and what is unknown. Let us remember the following important facts of a horizontally launched projectile. First, we have the horizontal motion of a projectile is independent of its vertical motion. Second, there are no horizontal forces acting upon projectiles and thus no horizontal acceleration. Third, the horizontal velocity of a projectile is constant, a never-changing in value. Fourth, there is a vertical acceleration caused by gravity. Its value is 9.8 meters per second squared down. And lastly, the vertical velocity of a projectile starts with 0 meters per second and changes by 9.8 meters per second each second. Now, to best illustrate, let's take a look at this cannonball here. Let's take a look at this launching a cannonball from top of a very high cliff with an initial velocity of 20 meters per second. Let us focus on the horizontal motion. And neglecting air resistance, the cannonball, as you notice, will continue in motion at 20 meters per second. That's what you can see. This is actually consistent with the law of inertia, which states that when an object is at rest, will remain at rest, and if an object is in motion, will remain in motion unless acted upon by an unbalanced force. So, what can you infer with this? So, it is very important to note that for our x component, our initial velocity here will be the same with our final velocity. So therefore, our initial velocity is equal to our final velocity. Second, there is no horizontal acceleration. Therefore, our acceleration for x component would be 0 meters per second squared. Now, let's proceed to the vertical component. Now, as mentioned earlier, projectile motion is a motion which is the only force acting on it is gravity. Now, let's focus on the vertical component. As what you've noticed, the displacement, this one here, this is your y component displacement. And based on your observation, there is actually a change of 9.8 meters per second each second. You may wonder as to why this happened. Again, this is because there is a force acting upon our vertical component, and that's the gravity, which is equivalent to 9.8 meters per second squared. Now, you may notice that it has a negative value. Don't be confused about that. This is to indicate the direction is going down. So if you, if you relate it to your graph in your mathematics, the value on your y-axis going down is negative. So that is why we have here a negative value, considering that the direction is going down. So since any object affected by gravity goes down, so again, it has a negative displacement. Displacement again is a vector quantity, therefore it is a direction specific. So that's why we're putting negative on the y component. Now, what are the important things that we should remember for y component? So our initial velocity, of course, starts with 0. And since there is a force acting on the cannonball, that's the reason why each second there is a change of the displacement. So our acceleration for y component would be 9.8 meters per second squared. So again, let's review. For x component, initial velocity is equals to final velocity, and the acceleration for x component is 0 meters per second squared, while for y component, our initial velocity is 0 meters per second, and our acceleration is at 9.8 meters per second squared. Now, take note that these variables are constant regardless if it is given or not given in the problem. Before we solve any problem, let's again, for Kinematic Equation, we use this for any motion that can be described. For that is the projectile motion. Now, they're totally independent from each other. Therefore, we will be needing two sets of kinematic equations here. One for the x component and the other is for the y component. Now, if you take a look at this equation, we simply put an x variable here. This is to indicate that this is for x component. And then we put y subscript here. That would indicate that this equation is for the y component. Alright, so since we know the basic concept of a horizontally launched projectile, let's solve the problem. A ball is thrown horizontally out of the window with a velocity of 3.5 meters per second. If the window is 5 meters above the ground, how far will the ball travel before it hits the ground? Now, before we solve any given problem, going on with that problem. So let's imagine that this is the window, this is the ball, which is being thrown out from the window. First things first is to identify if we're talking about the vertical direction, vertical motion, or the horizontal direction, or the horizontal motion. So again, for vertical direction or motion, this is varog, and for the horizontal motion or horizontal direction, this is higda. So just use that to avoid. Now, what is being asked in the problem? So what is asked in the problem is how far will the ball travel before it hits the ground? So we're talking about the distance of the ball from here going here. So this is a horizontal direction. Therefore, we're looking for the displacement x. Now, it is also given the initial velocity. The initial velocity of x component, which is 3.5 meters per second. So when that person threw the ball out of the window, its initial velocity is 3.5 meters per second. So remember that there is no initial velocity for a vertical motion when we talk about horizontally launched projectile. So therefore, our initial velocity given here is for the x component. So we have here 3.5 meters per second, and based on the law of inertia, our initial velocity is actually equal to the final velocity. And remember that since the velocity is not changing, therefore there is no force acting upon the ball. And you can infer that there is 0 meters per second squared acceleration for the x component. Now, let's proceed to the y component. What is given in the y component is, of course, the displacement y. This one here, that's varog. So that's displacement y, that's 5 meters. And as you all know, since the cannonball reached the ground, therefore, there is a force acting upon that ball, and that's the gravitational force, which is amounting to 9.8 meters per second squared. So that's our acceleration y. And for our initial velocity, that's 0 meters per second, as mentioned earlier on our basic concept. And we don't have any given final velocity. Now that we have all the given variable in the problem, and we also know the what is asked in the problem, let's proceed to how we can solve this problem. So again, we have two sets of formula here. We have for x component, and we also have for y component, since again, they're totally independent from each other. Now, since there are actually four equations, we need to only use one. So, of course, how can we choose a kinematic equation out of that four? So, it's very important for us to decide which is the best equation. And that would only be possible if we know the given and what is asked in the problem. Now, again, what is asked in the problem is the displacement x. So the best formula we can use for this is this one. dx is equals to bix times time plus 1/2 times acceleration x times time squared. That's the best formula we can use out from those four if we talk about the x component. However, we cannot directly solve dx. Why? Because we don't have a value for time. So we need to determine what is the value of time before we can proceed in solving the displacement x. So how can we do that? Now let's take a look at the y component here. And then we look on what is given. So we have here dy, we have acceleration, we have initial velocity. So let's take a look at each equation. How can we solve time? Can we? Yes, of course we can. And the best equation we can choose is this one. Y. We have a displacement y, that's 5 meter. We have initial velocity, which is 0 meter per second. We have acceleration due to gravity, which is 9.8 meter per second squared. So therefore, we can actually solve for time if we use this equation. And if we simplify this equation, we can actually come up to a more easy computation, and that's time is equal to the square root of 2 displacement y over gravity, which is 9.8 meter per second squared. Now let's continue to solve. Again, this is actually the formula that we will use to solve time, and this is the simplified version. So you can either choose any of the equation. This will give you the same answer. So let's substitute. So dy, that's 5 meter. Again, you can actually check earlier slide. And then we have 0 meter per second. This is for our initial velocity for vertical motion times time plus 0.5. I use 0.5 here because this is easier compared to 1/2. But again, it would really depend on which you're comfortable with. And then I multiply it with the acceleration due to gravity, which is 9.8 meter per second, and times time squared. Now I cancel here 0 meter per second times time, since there's no value. Whatever you multiply by 0 will be 0. So that would actually give us 5 meter is equal to, we multiply this two variable here, so that's 4.9 meter per second t squared, and then you simply divide both sides with 4.9 meter per second squared, so we can cancel the value here. So t squared is equals to 1.02 seconds squared, and then you simplify it, you squared both sides, and you will come up to the answer, which is time is equal to 1 second. Now that we know the value of time, which is 1 second, we are now ready to solve for the displacement x. So this is actually the best, or this is actually the equation we chose earlier to find the displacement x. So we simply substitute. So dx, which is as in the problem, is equals to 3.5 meter per second. This is our initial velocity for x component, plus 0.5 times 0 meter per second squared. Okay, remember this one. Times our time earlier, which is 1 second. So you simply count as 0.5 times 0. So you will end up multiplying 3.5 meter per second to 1 second. So therefore, our answer would be 3.5 meter for the displacement x. And that's it. That's how easy you can solve problems regarding horizontally launched projectiles. what you can see is a golf player hitting the ball. And as what you've noticed, he has different options on what angle will he hit the ball. Now, based on the picture, which angle will give you the farthest range? That's right, it's the 45 degrees that will actually give you the highest, the farthest range. Now, what about 60 and 30 degrees? That's right, 30 degrees and 60 degrees will actually give you the same range. However, they only differ on the pick. 60 degrees has a higher pick compared to 30 degrees. Same goes with 75 degrees and 15 degrees. 75 degrees will have the highest pick among all angles given. However, if we talk about range, they're the same with 15 degrees, this one here. Now, didn't you know that this projectile concept are used for sportsmen as they play in the court? It may not be applicable to all sports, but sports such as baseball, basketball, soccer, etc. are just one of the sports where concept of projectile motions can be applied. Now, to solve problem regarding non-horizontally launched projectile, it is best to know what are the important facts. And let's define what is a non-horizontally launched projectile. So it is defined as a projectile that begins its motion with an initial velocity that is both horizontal and vertical. That means that non-horizontally launched projectile is different with horizontally launched projectile. This is because for horizontally launched projectile, our initial velocity is for the horizontal motion only, and it doesn't include the vertical motion. However, in the non-horizontally launched projectile, our initial velocity is for both horizontal and vertical motion. Let's go deeper with that concept later on. Second is an object is projected from rest at an upward angle. Third, its initial velocity can be resolved into components. Next, the horizontal velocity is constant. So the concept for horizontally launched projectile is also applied in non-horizontally launched projectile when it comes to its velocity. So whatever the initial velocity, that should be equal to the final velocity of the horizontal motion. Next is the acceleration is constant due to gravity. We're talking about the y component here. So for the y component, it will have a constant acceleration of 9.8 meters per second squared. Now, these are the, again, kinematic equations that we will be encountering, just like the horizontally launched projectile. So we have here for the x component and we have for the y component. Now, as mentioned earlier, for the initial velocity, it's going to be for both horizontal and vertical motion. So therefore, this is how we can solve or we can find the initial velocity for the x component. And this is the formula if we want to find the initial velocity for the y component. Now that we know the basic concept of non-horizontally launched projectile, then we are ready to solve. A ball is thrown with an initial velocity of 40 meters per second. This initial velocity makes an angle of 30 degrees with the ground. Find the following: maximum height or displacement y the ball can reach, the total time the ball is traveling through the air, the horizontal distance, that's displacement x, it hovers along the level ground, and resolve the initial velocity into vertical and horizontal components. Now, again, before we solve any problem, it's very important for us to imagine what's going on in that problem. So, imagine that this is actually our ball. So this is our ball, and this is the angle of release, that's 30 degrees. Now, we need to identify which is dy, or the displacement y, and the displacement x here. So it's very important for us again to look into the direction. So dy, this is actually a vertical direction, therefore this is our dy, and this is our displacement x, or this is also what we call as range. And for the ball, it, once it is launched 30 degrees angle from the time it is released going to the ground, this is what we call the total time. This one is the dy, this is the peak of the projectile. From the ball to the highest peak, we actually associate this one as T1, and then from the highest peak going to the ground, that's our T2. So T1 plus T2 is equals to the total time. Now, let's proceed to what is given and what is asked in the problem. And since, again, same goes with the horizontally launched projectile, non-horizontally launched projectile is a combination of the horizontal and vertical components. So we will have a separate given.
It's 8 o'clock.
For this two components. So for the initial velocity, again, for the non-horizontally launched projectile, this is for both the horizontal and the vertical velocity. So how can we get its initial velocity for x and its initial velocity for y? This is how we solve it. For finding the value for the initial velocity for x, we have initial velocity times cosine theta, or the angle of release. And then we also have how to find the initial velocity for the y component. We have the initial velocity times sine theta, or the angle of release. Now that we know our theta here, that's 30 degrees, right? So we are going to substitute. We also know our initial velocity, which is 40 meters per second. Now let's find the value of our initial velocity for the x component. So very simple, you simply substitute 40 meters per second times the value of cosine 30 degrees. You can check this on your scientific calculator, or you can actually check it on Google. Now, 40 meters per second times the value of cosine 30 degrees, which is 0.87, that would actually give you 34.8 meters per second. This is for our initial velocity for the x component. Now, for the initial velocity for our y component, we need to get the vi times the sine 30 degrees. So we have, again, the 40 meters per second is our initial velocity times the value of sine 30 degrees, where you can check on your calculator or on your Google, that would be 0.5. So that would actually give you 20 meters per second for your initial velocity for the y component. Solve this problem here. So let's proceed to what is asked and what is given on the problem based on the basic concepts that you learned earlier. So again, we have the initial velocity for the x component, which is 34.8 meters per second squared. And since for the horizontal velocity, it's constant. It is not changing. Again, the best explanation for that is the law of inertia. So the value for our initial velocity and our final velocity for the x component would be the same, just like in horizontally launched projectile. Same goes with our acceleration. Since the velocity is not changing, that would mean that there is zero acceleration. So that would be the given for our x component. And what's being asked here is actually the range, this one here, or the displacement x. That's our missing. So we need to solve that. Now, let's proceed to the vertical component or the y component. Now, our initial velocity as what we come up to earlier, that's 20 meters per second. And for our, of course, final velocity, that would be negative 20 per, that would be negative 20 meter per second. This is actually because of the symmetrical nature of a projectile's trajectory. You may check this illustration here. So that's the reason why our final velocity is negative 20 meters per second square, because of the symmetrical nature of projectile trajectory. And of course, our acceleration would still be constant at 9.8 meters per second squared, and the negative here indicates the direction, which is going down. And also, our total time is not given in the problem, so we also need to...
It's 10 o'clock.
Now that we know the value of our initial velocity for x component and initial velocity for y component, we are now ready to find for the maximum height the ball can reach. We will also be looking for the total time and the horizontal distance it covers along the level ground. Now for the maximum height dy, so this is actually our dy here, we will be looking for the maximum height. To solve that, again, we go back to the kinematic equation, and the best possible equation we can use is this one. That's displacement y is equal to initial velocity y times time plus 1/2 times the acceleration due to gravity, and it's negative here because we are direction specific for the non-horizontally launched projectile, times time squared. However, we cannot directly solve for the displacement y because we don't know the value of the time yet. So to know the value of time, we need to use another kinematic equation where we can find time based on what is given on our problem. So the best equation we can use is this one. So that's velocity, final velocity y, we have this one, that's negative 20 meters per second, due to the, again, that's because of the symmetrical nature of the projectile's trajectory. We have the initial velocity y as well, that's 20 meters per second, plus our acceleration. We have acceleration due to gravity. So definitely we have all the given to solve for time. So if we want to simplify this kinematic equation, we'll actually come up to this simpler version here. So we simply substitute. So time is equal to negative 20 meters per second. Again, this is negative because the direction is going down, and this is based on the symmetrical nature of the projectile trajectory. You can check the slides previously for this matter. And then we have here minus initial velocity y, which is 20 meter per second over, that's negative, that's for the direction since it's going down, 9.8 meter per second squared. So we're gonna come up to the total time of 4.08 seconds. That's our time from the ball before it releases going to the ground. So that's our total time. Now, since we have already the total time, we are ready to solve for the displacement y. So again, for the displacement y, this is the best kinematic equation we can use. Now we simply substitute. So dy here, that's what is as, is equal to the initial velocity y, that's 20 meter per second, times time. Our time here is 2.04 seconds. Why is that? Because again, we're looking for this one. Okay, so the time we need is just half of the total time. So that is why it is 2.04 seconds here. Again, we're only looking for the displacement y, it's the highest peak, and before the ball reached its highest peak, it would only take half of the time before it reached to the highest peak, before it reached the ground. So please take note of this for in finding our peak height, or in finding distance for the displacement for the y component. We just need to use half of the total time. So again, let's proceed. That's 2.04 seconds plus 1/2 of the acceleration, which is negative 9.8 meter per second squared. We're very particular with direction for the non-horizontally launched projectile, times 2.04 seconds squared. Again, we are going to use half of the total time in finding the displacement y. So we need to multiply, so that would be 40.8 meter plus negative 4.9 meter per second squared times 4.16 seconds squared. And then to simplify, we have 40.8 meter minus 20.38 meters. So our answer would be 20.42 meter for our displacement y. Now, we already have the total time, we have the displacement y, so we are ready to solve for the displacement x. So again, we go back to the kinematic equation, and the best equation we can use is this one here. Since we have already the initial velocity for our x, we have the time earlier, we have acceleration, so we're ready to solve. Now, to simplify this formula, we can use this one as well. Okay, this is a simpler version. And again, you will come up with the same answer. That would actually depend on which formula you are comfortable with. Now, displacement x is equal to our initial velocity for the x component, which is 34.8 meter per second earlier. And of course, for the total time, we will be using total time here because we're talking about the range here. Okay, so we will be using the total time compared to the displacement for the y, for the highest peak, that would only require half of the time. But if we talk about the range, the displacement x, we will be using, so that would be 4.08 seconds. So if we simply multiply, that would actually give us a displacement x, which is equal to 141.98 meters. So that's our total range. That's how far the ball traveled after it reached the ground. So, my dear students, I hope that this video would actually guide you in solving projectile motion, most specifically with horizontally launched projectile and non-horizontally launched projectile. I hope to see you soon. Have a nice day. Goodbye.